Okay, so welcome to this next video in which we are discussing thymidylate synthase inhibitors as anti-cancer chemotherapies. Okay, so we are in the process of looking at the folic acid pathway and how we produce N5-N10 methylene tetrahydrofolate. And the reason we're doing that is because it's a very important substrate for the thymidylate synthase enzyme, and we can't really understand what the thymidylate synthase enzyme is doing until we understand the folic acid biosynthesis pathway. Okay, so to understand how the thymidylate synthase inhibitors work, we need to understand how thymidylate synthase works, and that's why we are looking at this pathway. So we have so far got to dihydrofolate, and we're now going to convert that into tetrahydrofolate. So one more structure. In fact, no, it's not the. I'm afraid it's not the last structure, but we're just drawing out the same thing again, so it should just be nice revision. Okay, so here's the carbonyl group here, and then we've got the nitrogen down here. Oops. Okay, let me remove this. Oh, it's nicely in view already. Right, so we've got a double bond here and a double bond here. We've got an amino group off here. Okay, and a hydrogen off this nitrogen here. Now, this pyrazine ring has been reduced again, so it's got two new hydrogens off it. So this nitrogen has a hydrogen off it. This nitrogen already had a hydrogen off it in dihydrofolate. And in addition, this carbon here will also have an additional hydrogen off it. But of course you don't show that because we're drawing a skeletal structure here. So then you have the methylene group with the nitrogen up here, with the hydrogen off it. Then you've got your benzene ring up here. Okay, with the alternating double and single bonds. The carbonyl group up here involved in this amide link with the glutamic acid amino acid over here. Okay, so here's the carboxylic acid group of the glutamic acid molecule, and then here's the R group of glutamic acid. Okay, and there we go. Right. Okay, so this is the structure of tetrahydrofolate. Okay, and by the way, tetrahydrofolate is often abbreviated to THF for short, so often hear that abbreviation, THF, and dihydrofolate is often abbreviated to DHF. Okay, right. So, what are we going to do next? Well, basically, we are going to convert this into something known as N5-N10 N5-N10 methylene tetrahydrofolate. Okay, so let me just write this name out. Okay, so N5-N10 methylene, and then tetrahydrofolate. Okay, so on to the other next line. And of course, tetrahydrofolate should ideally be one word, but of course I ran out of space. Okay, so N5-N10 methylene tetrahydrofolate. And to understand what on earth that molecule is, we need to understand the numbering system of the the elements in this structure. So we start off with this N here, and we call that the first member of this structure. Then we label this carbon here 2, this nitrogen here 3, this carbon up here 4, this carbon here 4A, because it's in both rings, it doesn't get a new number itself. This N here is 5, this carbon here is 6, this carbon here is 7, this N here is 8, this carbon here is 8A, this carbon here is 9, this nitrogen here is 10, and we don't need to go on any further. So, we now know where N5 is, and we know where N10 is. So what we're actually going to do is stick a methylene group in between this nitrogen and this nitrogen. So all we actually need in order to do that is a carbon atom providing, basically. So if you just bring in one carbon atom, a pure carbon atom, so not bound to anything with no charge, the carbon atom has 4 electrons in its outer shell. All you then need to do is cut this bond here, and you can imagine that one electron will go back to the hydrogen, one to the nitrogen, one electron to the hydrogen, one to the nitrogen here as well. And then what you'll do is each of these nitrogens will have a lone electron basically, and each of these nitrogens can then bind to that hydrogen atom and form a single covalent bond, and also these two hydrogens can then bind to the carbon. So what you're effectively going to do is, if you put the carbon in the middle here, this nitrogen down here, nitrogen 5 is going to bind to it, nitrogen 10 is going to bind to it, and both of these hydrogens are going to bind to it, because all four of these species have lone electrons. The carbon then has 4 outer shell electrons, so it can give 1 to each of these and then get a nice shell of 8 basically, and then it's nice and happy. Okay, so that's what we're going to do. We just need a carbon atom to come in here, and then what we're going to do basically is have another ring there now. Okay, so let me just go over the page and draw the structure of N5N10 methylene tetrahydrofolate. So N5N10 methylene tetrahydrofolate. Tetrahydrofolate, and this is the final thing that we're going to need. Okay, so N5N10 tetrahydrofolate. Oh, sorry, N5N10 methylene tetrahydrofolate. So we start off again with our pyrimidine ring over here. Okay, with these 2 nitrogens like so, and these 4 carbons. Whoops, and then we have our carbonyl group up here. Okay, we have our double bond here and the double bond here. We have a hydrogen off this nitrogen and an amino group off this carbon. Okay, and then onto this next ring we then have our, what's left of the pyrazine ring, but it's not much of a pyrazine ring anymore. Okay, and you have a hydrogen off this nitrogen, but we know of course it's changed. The situation with this nitrogen has changed. You then have your methylene group, you have this nitrogen, and now you have a carbon in between here, which we know is a methylene group. So this carbon also has 2 hydrogens bound to it, but of course this is a skeletal structure, so you don't show that. Then this nitrogen has a benzene ring bound to it, and now I'm going to have to squash things in because otherwise we're not going to fit everything on here. And then this benzene has the carbonyl group off it, okay, which is bound via an amide link to our glutamic acid over here. Okay, so then we have our carboxylic acid group coming up here, which should be an oxygen there, and the alcohol group here. Okay, and then we have the R group of the glutamic acid, so 2 methylene groups, then a final carbon here which will have the oxygen double bound to it, and the alcohol group coming off here. Okay, so that is N5N10 methylene tetrahydrofolate. Okay, right, so you go from folic acid to dihydrofolate to tetrahydrofolate to N5N10 methylene tetrahydrofolate. Now, this is what we're going to need in order for thymidylate synthetase to work. So, what does the enzyme thymidylate synthetase do? Well, the clue is in the name, thymidylate synthetase. Don't like this word. Right, it's going to synthesize thymidylate, but what is thymidylate? Okay, so let me explain what thymidylate is. So thymidylate is the name for the organic base thymine, okay, plus a deoxyribose sugar, okay, deoxyribose, and then finally plus a phosphate group. Okay, so let me show you the structure of this. Phosphate. Okay, so let me show you the structure of this. So basically it's a nucleotide. Thymidylate is the thymine DNA nucleotide. So we'll start off with the deoxyribose. Okay, so we'll draw skeletal structures again. So here is our ribose, the 5-membered ring where 4 of the members are carbons and this top member is an oxygen. Okay, and then you have the 5th carbon coming off up here, which then has an alcohol group attached to it, but this alcohol group has a phosphate group attached to it. And I hope this is all going to fit in. Okay, it's just fitting in there. So a phosphate group is this phosphorus atom at the centre with a double bond to an oxygen, then an alcohol group really off both sides, but of course one of these alcohol groups has been involved in the formation of this phosphoester link between the alcohol group of the 5th carbon of deoxyribose and the alcohol group of the phosphate group. Okay, and then you've also got this single bond to an oxygen down here, which has acquired an electron ionically and therefore has a negative charge. Okay, now there's an alcohol group also of the 3rd carbon down here, but because we're talking about deoxyribose, it doesn't have an alcohol group of this 2nd carbon, so we're talking about the sugar that is within DNA, not RNA. In RNA you have ribose, and ribose does have another alcohol group of that 2nd carbon. In DNA you have deoxyribose, which more pedantically is called 2-deoxyribose to indicate that the alcohol group has been taken off this 2nd carbon. Okay, now thymidylate is the DNA nucleotide for thymine, and that makes sense because if you remember back to your basic central dogma of biology, there is no thymine in RNA, so you would not want thymine linked to ribose. Okay, so it's always going to be about deoxyribose because thymine is reserved for DNA. Okay, so then this 1st carbon here is linked to the actual thymine organic base here, and thymine is a pyrimidine, so we're going to see pyrimidines again. So basically it has these 2 nitrogens. You have a nitrogen off here, but most of the alternating double and single bonds have been destroyed again. So you've destroyed the one between this nitrogen and this carbon by again putting a carbonyl group there, and you've also destroyed the one between this nitrogen and this carbon again by putting a carbonyl group there. Okay, but you still do have the alternating double and single bond, sorry, you do have the double bond here. And then you finally also have a methyl group off there. So that's the structure of the thymine organic base. Okay, so this is thymine plus deoxyribose plus a phosphate group. This is thymidylate. Now thymidylate also has another name. It's also referred to as thymidine monophosphate. Okay, so thymidine means thymine plus deoxyribose. Okay, and I'll discuss this more in the next video.